Hi, I'm Michael Gardner, and this is Vortex Tubes, Modeling, Operation, and Performance, a CFD story. For some background, we go back to 1867 when James Clerk Maxwell gave a hypothetical situation where we could use a small demon to guard an aperture between two chambers, and he would selectively let high energy particles through to the hotter chamber and keep the cold particles out, and therefore the energy would move from low to high. And vortex tubes have a similar operation, but they do keep the second law intact in the form of a work input of pressurized air. And that can allow temperatures from negative 50 degrees C at the cold end to 200 C at the hot end. And just looking over some structural stuff at the bottom here, you can see these three main parts, which are the generator, the compressed air supply in the body, and the hot air exhaust valve. So the generator is the most tricky part. It turns this single compressed air supply into 6 tangential inputs into this vortex tube. So if we extract that flow domain, you can see those 6 tangential inputs from that generator, and you hit play on this. And what you'll see here is some of these particles will form this counter-rotating vortex in the middle because they're low energy, but these high energy ones are going to shoot out the side when they get to the end. And again, the low energy ones are just going to drift down the other way out to that cold outlet. And so for the pre-analysis and governing equations, obviously the expectation is that we're going to have a couple different vortices form, and that there will be a significant temperature separation that occurs between the outlets. I used turbulent flow, specifically the K omega SST turbulence model. It deals well with shear stress forces and utilizes the continuity X, Y, and Z momentum equations, turbulent kinetic energy, specific dissipation rate, and energy equations. And I actually tried the Reynolds stress model and the K epsilon model, and K epsilon didn't work. Reynolds stress worked, but it is like a 5 or 7 equation method, and so it's a lot more computationally intensive. So K omega SST worked, and I could run a lot more iterations with it. My mesh was actually relatively coarse compared to what I thought it would have to be. It's about 40,000 nodes, a little over 200,000 elements of tetrahedral cells, and maximum element size was 2.75 millimeters. And the average skew was 0.21, and actually the max skew was 0.8. I set up the physics by first setting the K omega SST model, turning the energy equation on. Kept the materials as air and aluminum, but I did set the air density to ideal gas, since compressibility is a huge factor in the proper operation of this device. For the boundary conditions, I did a mass flow inlet. The temperature of that inlet was 294.2 degrees Kelvin. At the cold outlet, I made that a pressure outlet with a static pressure of 15,000 pascals. The hot outlet is also a pressure outlet, but I varied that one depending on the mass fraction that I wanted, in that particular scenario. And after 2,000 iterations, convergence was pretty loose, so I ran it again with temperature monitors so that I could see that convergence was happening and that it was a relevant solution. And I saw, if we just look at the average temperature values at each face, about a 59 degree temperature separation, which is good. And with different geometric properties like length over diameter ratio, different like outlet dimensions, changing the mass fractions, you can manipulate the hot and cold extremes so that you can achieve either lower temperatures at the cold end, higher temperatures at the hot end, or if you want the best mix of mass flow rate and low temperature, you're going to get the highest refrigeration value if you're looking to cool something. Also notice that blue section here is actually a cold vortex that's rotating counter to that hot vortex, just like we saw in the animation earlier. Another picture, we have a cut plane that shows separation of air particles by high and low energy levels. And obviously the minimum at the cold exit and the maximum at the hot exit is going to be way higher than our average temperature separation. And it's about 98 degrees Kelvin. And this is all within a tube that's about 4 inches long. So it's definitely a pretty sharp temperature gradient. Again, the residuals didn't converge very tightly after 2,000 iterations. And as you can see, Omega kind of threw a couple tantrums in here. So I set some monitors just to see what was actually happening in the system. And we can see that the hot outlet ends up being the highest temperature in the system, and the inlet ends up being in the middle, and the cold outlet ends up being the coldest. So great. And then to further validate that, I checked it against a paper by Mahmood et al. And compared it to their results. And I did use the same L over D ratio that they used, but was not sure what they did on as far as their outlet pressure on the hot end, or what area was open for flow, stuff like that. So not knowing that, I'm actually really surprised I got as close to them as I did. They had about 61 degrees difference. I had about 59. My results are shifted a little lower on each end. And they used K epsilon, which again didn't work for me. So I'm not entirely sure. That could be a meshing thing, or some of those other geometric and pressure differences that I was talking about. Some of the challenges here were just 3D models are pretty limited as far as how you can utilize them with the student version of ANSYS. You only get 500,000 cells. I ended up not getting too close to that and getting good results, but I do think I could get better results and trust my results a little more if I could confidently get more cells. One thing that I would do if I had to do this project again was I'd do periodic boundary conditions. It allows for, I could split this thing into 60-degree arcs and use a periodic boundary condition to essentially match the topography on this mesh. If you look, it's exactly mirrored across that vertex in the front. And that would allow the program to, for one side to communicate with the other as though they were continuous. And so you could get the exact same results with a way finer mesh, or you could use the same mesh and have a lot less computation to execute. The other challenge here is that the Rance equations can be very sensitive in high swirl situations. And some of the more complicated ones, like the Reynolds stress model, which is not a 2-equation model, has a little bit more complexity to it, and it can be a little bit more sensitive to the inputs that you are utilizing. So the K omega SST was definitely the best balance of that as far as simplicity for a novice. And in the future, along those lines, I kind of want to do some more simulations with a periodic boundary, a finer mesh, see if I get consistent results, or if I'm going to get closer to the results that Mahmood and all of them got. I want to see what happens if I manipulate the mass fraction, see what the maximum refrigeration I can get is, see how my swirl velocities compare to theirs. And I'd like to learn more about the different turbulence models, because again, I stuck with K omega because it was the simplest that gave me the results I needed. But the Reynolds stress model is supposed to be very good for swirl applications. So, having that in my toolbox I think would be very useful. And I would like to utilize a vortex tube in a transient heating simulation to see the effect of spot cooling. This is actually in line with some of the research that I'm doing, so there's a direct application for me. And here are some references in case you're curious. Really, it's just that last one is the paper. The other two are pictures, but I'll take any questions you got now.